In the infinite vastness of space, imagine a world unlike any you've known before. A planet cast adrift in the cosmic ocean, eternally wandering through the darkness between the stars. No sun to warm its surface, no celestial dance of orbit to give it rhythm, no place to truly call home. These aren't creatures of science fiction, they are very real celestial nomads, known as rogue planets or orphan worlds. Picture a massive gas giant, perhaps several times larger than Jupiter, hurled from its original solar system by a violent gravitational encounter. Or envision a rocky world, not unlike Earth, torn away from its parent star by the gravitational pull of a passing stellar neighbor. These cosmic castaways now traverse the galaxy in perpetual twilight, their surfaces forever shrouded in eternal night. Scientists estimate that our Milky Way could harbor billions of these mysterious wanderers. Some may have been violently ejected from their birthplaces during the chaotic early days of solar system formation. Others might have broken free when their parent stars died in catastrophic explosions. Each rogue planet carries with it a unique story of cosmic survival, drifting silently through the interstellar void. These lonely worlds challenge our traditional understanding of what it means to be a planet. They defy the conventional image of planets as faithful companions to stars, instead charting their own solitary paths through the galaxy. Their discovery has opened up new frontiers in astronomical research and forced us to reconsider our theories about planetary formation and stellar system dynamics. As we turn our most powerful telescopes toward the darkness between the stars, we're beginning to uncover more and more of these enigmatic objects, each one adding another piece to the puzzle of our cosmic neighborhood. Their study offers unprecedented insights into the violent processes that shape our galaxy and the countless worlds it contains. So join us on this fascinating journey as we explore the science behind these cosmic wanderers, uncover the methods astronomers use to detect them, and contemplate what these nomadic worlds might tell us about our own place in the universe. If you're as fascinated by these cosmic wanderers as we are, don't forget to hit that like button and subscribe to Exploring the Universe. Together, we'll continue to uncover the mysteries of space, one celestial secret at a time. Click the notification bell to ensure you never miss our next astronomical adventure. Your support helps us bring more of these incredible cosmic discoveries right to your screen. Now, let's dive deeper into the mysterious world of rogue planets. Deep in the cosmic wilderness, far from the warmth of any star, exists a remarkable category of worlds that challenge our understanding of planetary science. These are rogue planets, also known as free-floating or orphan planets, celestial bodies that have broken free from the gravitational bonds that typically tie planets to their parent stars. To truly understand rogue planets, we must first define their unique characteristics. These celestial wanderers are planetary mass objects, ranging from small rocky bodies similar to Earth to massive gas giants several times the size of Jupiter. What sets them apart is their solitary nature. They don't follow an orbit around any star, making their own way through the vast expanse of interstellar space. The mass of these nomadic worlds is crucial to their classification. They must be massive enough to achieve a roughly spherical shape under their own gravity, yet not massive enough to initiate nuclear fusion in their cores, the defining characteristic that separates planets from stars. This places them typically between 0.08 and 13 times the mass of Jupiter. However, establishing precise boundaries can be challenging, as there's often a blurry line between massive rogue planets and brown dwarfs, which are failed stars. Unlike traditional planets that receive energy from their host stars, rogue planets must rely solely on their internal heat for any energy output. The youngest and most massive of these worlds may still glow faintly in infrared light due to the heat left over from their formation, while older or smaller ones are likely frigid bodies drifting through the cosmic darkness. What makes these worlds particularly intriguing is their potential origin stories. Many scientists believe that most rogue planets began their existence as normal planets within star systems. Through various astronomical events, such as gravitational interactions with larger planets, close encounters with passing stars, or the death of their parent star, they were violently ejected into interstellar space. Some may have formed directly from collapsing clouds of gas and dust, never having been part of a stellar system at all. Recent studies suggest that these cosmic outcasts might be surprisingly common. Conservative estimates indicate that there could be billions of rogue planets in our Milky Way galaxy alone, potentially even more numerous than the stars themselves. This abundance raises fascinating questions about planetary formation and the dynamic nature of galactic evolution. The journey of a planet becoming a cosmic wanderer is a tale of celestial violence and cosmic circumstance. There are several fascinating pathways through which a planet can be cast into the solitude of interstellar space, each representing a different kind of astronomical drama. The most common mechanism is gravitational ejection, a cosmic dance gone wrong. Imagine a young solar system, still in its turbulent youth. Multiple planets orbit their star, their gravitational pulls constantly tugging at one another. In this celestial ballet, larger planets can act as cosmic bullies, their powerful gravitational fields disrupting the orbits of smaller worlds. When two planets pass particularly close to each other, one might receive enough of a gravitational boost to reach escape velocity, breaking free from its star's gravitational grip. This process is particularly common in systems with gas giants, whose immense gravitational influence can send smaller planets hurtling into interstellar space. Another scenario involves close encounters with passing stars. As stars move through the galaxy, they occasionally pass near other solar systems. These stellar flybys can be catastrophic for planetary orbits. The gravitational force of the passing star can tear planets away from their home systems, either capturing them into new orbits or launching them into the void of interstellar space. Computer simulations suggest this scenario might be surprisingly common in dense stellar neighborhoods, such as young star clusters. The death of a host star represents another dramatic path to planetary liberation. When massive stars end their lives in supernova explosions, the violent outburst can literally blow their planetary systems apart. The sudden loss of the star's mass, combined with the explosive force of the supernova, can send planets careening into interstellar space. Even less violent stellar deaths can lead to planetary ejection, as stars like our Sun evolve into red giants and eventually white dwarfs. The changing gravitational dynamics can destabilize planetary orbits. Perhaps most intriguing is the possibility of direct formation. Some rogue planets might never have known the warmth of a parent star. In the depths of molecular clouds where stars are born, smaller clouds of gas and dust can collapse under their own gravity to form planetary mass objects, without gathering enough material to trigger stellar fusion. These objects, born free of any star's influence, begin their lives as cosmic wanderers. Recent research suggests that rogue planets might even form in the aftermath of stellar collisions. When two stars merge or interact violently, the resulting debris field could potentially coalesce into planetary mass objects that are ejected into interstellar space. The process of becoming a rogue planet also has profound implications for these worlds. Planets violently ejected from their systems might retain some of their original characteristics: atmospheric composition, internal heat, and even moons. Those formed in isolation might have very different properties. Understanding these different formation mechanisms helps astronomers piece together the complex puzzle of planetary evolution and galactic dynamics. Hunting for rogue planets presents astronomers with a unique challenge. How do you find a dark, cold object floating in the vast emptiness of space? Among the various detection techniques available, gravitational microlensing stands as one of the most powerful tools in our astronomical arsenal. Gravitational microlensing relies on one of Einstein's most profound insights: massive objects bend light. When a rogue planet passes precisely between Earth and a distant star, it acts like a cosmic magnifying glass. The planet's gravity bends and focuses the starlight, causing the background star to temporarily appear brighter to observers on Earth. This astronomical phenomenon creates a distinctive light curve, a pattern of brightening and dimming that tells us not only about the existence of the rogue planet, but also provides crucial information about its mass. The beauty of microlensing lies in its sensitivity. Unlike other detection methods, it can identify extremely low-mass planets, potentially even as small as Mars. This sensitivity makes it our primary tool for discovering Earth-sized rogue planets drifting through the galaxy. The technique works regardless of whether the planet emits any light of its own, making it particularly valuable for finding older, cooler rogue planets that would be invisible to conventional telescopes. Each microlensing event tells its own unique story. The shape of the light curve reveals details about the lensing object. A sharp, brief brightness spike might indicate a small, fast-moving planet, while a longer, more complex pattern could suggest a larger world, possibly even one with its own moons. Advanced analysis of these light curves can even provide hints about whether the planet retains an atmosphere. However, microlensing comes with significant challenges. These events are exceedingly rare, requiring precise alignment between the background star, the rogue planet, and Earth. When they do occur, they're one-time events. The cosmic alignment never repeats in exactly the same way. This makes follow-up observations impossible, leaving astronomers with just one chance to gather all possible data. To maximize the chances of catching these rare events, astronomers have developed sophisticated observation networks. Projects like OGLE and KMT-net maintain continuous surveillance of dense star fields, particularly toward the galactic center, where microlensing events are most likely to occur. The future holds even more promise for microlensing discoveries. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will dramatically improve our ability to detect rogue planets through microlensing. Operating from space, free from atmospheric interference, it will provide unprecedented sensitivity to these cosmic wanderers. While gravitational microlensing helps us detect older, colder rogue planets, direct infrared observation opens a window into the world of young, massive cosmic wanderers. This method represents one of our most powerful tools for not just detecting, but actually studying these mysterious objects in detail. Young rogue planets, particularly those with masses several times that of Jupiter, retain significant heat from their formation process. This residual heat causes them to glow faintly in infrared wavelengths, much like a cooling ember continues to radiate in the dark. While these planets are far too faint to see in visible light, modern infrared telescopes can detect their thermal signatures against the cold backdrop of space. The James Webb Space Telescope has revolutionized our ability to study rogue planets through infrared observation. Its unprecedented sensitivity and advanced spectroscopic capabilities allow astronomers to not only detect these wandering worlds, but also analyze their atmospheric composition. The telescope's NIRCam and MIRI instruments can capture light from different infrared wavelengths, providing crucial data about temperature, size, and chemical makeup of these distant objects. When we observe a rogue planet in infrared, we're essentially creating a heat map of its atmosphere and surface. Different chemical compounds absorb and emit infrared radiation in unique ways, creating distinctive spectral fingerprints. This allows astronomers to determine whether a rogue planet has an atmosphere and, if so, what gases it contains. Some young rogue planets have been found to possess complex atmospheres with compounds like methane, water vapor, and carbon dioxide. Ground-based telescopes equipped with advanced adaptive optic systems also play a crucial role in infrared observation. Facilities like the Very Large Telescope in Chile and the Keck Observatory in Hawaii can pierce through Earth's atmospheric interference to study these objects. They often use coronagraphs, specialized instruments that block out the bright light from nearby stars to better observe faint planetary objects. However, direct infrared observation comes with significant limitations. The method works best for young planets, typically less than 100 million years old, as older planets have generally cooled too much to emit detectable infrared radiation. Additionally, the planets need to be relatively close to our solar system, usually within a few hundred light years, for our current telescopes to detect them. The size of the planet also matters significantly. Current technology primarily allows us to observe rogue planets that are several times more massive than Jupiter. Smaller, Earth-sized rogue planets are still beyond our current infrared detection capabilities, although future telescopes may change this. Despite these limitations, direct infrared observation has led to some remarkable discoveries. It has helped identify several free-floating planetary mass objects in nearby young star clusters, providing valuable insights into how these objects form and evolve. Each observation adds to our understanding of these cosmic outcasts and their role in galactic evolution. Astrometry represents one of the most sophisticated methods in modern astronomy, serving as our cosmic GPS for tracking objects moving through space. This technique, which measures the precise positions and movements of celestial bodies, has emerged as a powerful tool in the hunt for rogue planets. At its core, astrometry involves creating incredibly detailed maps of how objects move across the sky over time. Unlike stars, which generally follow predictable paths determined by our galaxy's rotation, rogue planets exhibit distinctive random motions through space. These wandering worlds don't conform to typical stellar movement patterns, making their irregular trajectories a telltale sign of their free-floating nature. The European Space Agency's Gaia spacecraft has revolutionized astrometric detection of rogue planets. This space observatory creates the most precise three-dimensional map of our galaxy ever attempted, measuring the positions of billions of objects with extraordinary accuracy, down to micro-arc seconds, equivalent to measuring the width of a human hair from 1,000 kilometers away. This unprecedented precision allows astronomers to detect the subtle movements of planetary mass objects drifting between the stars. Modern astrometric techniques combine multiple wavelengths of observation, from visible light to infrared, to build comprehensive movement profiles of celestial objects. By analyzing an object's proper motion, its movement across the sky, and parallax, its apparent change in position when viewed from different points in Earth's orbit, astronomers can determine its distance, velocity, and mass. The power of astrometry lies in its potential for large-scale discoveries. Unlike other detection methods that rely on chance alignments or specific conditions, astrometry can simultaneously monitor vast regions of space, potentially identifying numerous rogue planets in a single survey. This makes it particularly valuable for understanding the population statistics of these cosmic wanderers. However, the challenges of astrometric detection are significant. The precision required to detect planetary mass objects is extraordinary. Even minor atmospheric disturbances or instrumental variations can mask the subtle signatures of rogue planets. This is why space-based observatories like Gaia are so crucial. They operate above Earth's atmosphere, free from its distorting effects. The future of astrometric detection looks promising. Next-generation telescopes and improved computational techniques will enhance our ability to spot these elusive objects. Machine learning algorithms are being developed to sift through the enormous amounts of astrometric data, identifying potential rogue planet candidates for further investigation. Are you as captivated by these wandering worlds as we are? If so, don't forget to smash that like button. Here's an interesting question for you. If you could name a newly discovered rogue planet, what would you call it and why? Let your imagination roam as freely as these nomadic planets do. Share your creative names in the comments below. We'd love to hear the stories behind them. Remember to subscribe to Exploring the Universe and hit that notification bell to stay updated on more fascinating space discoveries. Your engagement helps us continue bringing the wonders of the cosmos to your screen. Now, let's journey forward to explore what these mysterious wanderers can teach us about planetary formation. The discovery and study of rogue planets has revolutionized our understanding of how planetary systems form and evolve. These cosmic wanderers serve as natural laboratories, providing crucial insights into the complex processes that shape our universe's planetary systems. Let's begin with the dynamics of young planetary systems. The very existence of rogue planets tells us that the early life of a solar system is far more chaotic and violent than previously imagined. During their formation, planetary systems undergo a period of intense gravitational interactions, much like a cosmic game of billiards. The significant number of rogue planets we've discovered suggests that planetary ejection is not a rare accident, but rather a fundamental aspect of system evolution. This realization has forced astronomers to revise their models of planetary system formation, acknowledging that many systems may start with more planets than they ultimately retain. The efficiency of planetary formation becomes clearer when we study the population of rogue planets. Current estimates suggest that there could be billions of these wanderers in our galaxy alone, possibly even outnumbering stars. This abundance reveals that planetary formation is a remarkably efficient process, capable of producing numerous worlds across a wide range of masses. However, it also indicates that maintaining stable planetary systems is more challenging than previously thought. The high number of ejected planets suggests that achieving the delicate gravitational balance required for long-term stability is a precise and often unsuccessful process. Perhaps one of the most valuable insights comes from studying the mass distribution of rogue planets. We've found these wanderers in various sizes, from small rocky bodies to massive gas giants. This distribution provides a unique window into the planet formation process itself. The relative abundance of different-sized rogue planets helps astronomers understand which planetary masses are most commonly formed in protoplanetary disks. This information is particularly valuable because it's unbiased by the selective forces that determine which planets remain in stable orbits around stars. The composition of rogue planets serves as a time capsule, preserving information about the environments where they formed. When we study a rogue planet's atmosphere or composition, we're actually examining the conditions that existed in its birthplace within a protoplanetary disk. This has helped astronomers map out the chemical and physical conditions in different regions of planet-forming disks, improving our understanding of how planets acquire their characteristics during formation. Additionally, rogue planets challenge our traditional definition of what constitutes a planet. Their existence raises fascinating questions about habitability and the potential for life in the universe. Some scientists speculate that rogue planets might retain heat through internal processes, potentially harboring subsurface oceans that could support basic forms of life, even without the energy input from a host star. The study of rogue planets has also revealed surprising information about the role of brown dwarfs and failed stars in planetary formation. The boundary between very massive rogue planets and very small brown dwarfs has become increasingly blurred, suggesting a possible continuum in the formation processes of these objects. The existence of rogue planets opens fascinating possibilities in our search for life beyond Earth, challenging traditional concepts of habitability while presenting unique scenarios for potential life-sustaining environments in the cosmic wilderness. Perhaps one of the most intriguing possibilities lies in the potential for massive rogue planets to harbor habitable moons. Much like Jupiter's moon Europa in our solar system, large rogue planets might maintain systems of moons that could sustain subsurface oceans through tidal heating. As these planetary bodies travel through space, the gravitational interactions between the planet and its moons generate friction within their cores, producing heat that could maintain liquid water beneath icy surfaces. These subsurface oceans, protected from the extreme cold of interstellar space, might provide stable environments where simple life forms could potentially develop and survive. Massive rogue planets, particularly those several times larger than Jupiter, possess another intriguing characteristic: their ability to retain substantial atmospheres. These thick atmospheric blankets could act as insulating layers, trapping internal heat and potentially creating more moderate conditions than one might expect in the depths of interstellar space. Some scientists theorize that certain atmospheric compositions might even create greenhouse effects powerful enough to maintain liquid water on the surface of some rogue planets or their moons, though such scenarios would likely be rare. The internal heat of young rogue planets presents another avenue for potential habitability. Newly formed planets retain significant heat from their formation process, and larger ones might maintain this warmth for millions or even billions of years through radioactive decay and gravitational compression. This internal heat could theoretically support deep biospheres similar to the extremophile communities found in Earth's deep crustal environments. However, the development of life on starless worlds faces formidable challenges. Without a host star's energy input, most rogue planets would be incredibly cold on their surfaces, with temperatures approaching absolute zero. This extreme cold would likely freeze most common solvents, including water, making conventional biochemistry as we know it extremely difficult. The absence of a day-night cycle and seasonal variations, which play crucial roles in many of Earth's biological processes, could also pose significant obstacles for the emergence of complex life forms. The lack of photosynthesis presents another fundamental challenge. Life on Earth relies heavily on solar energy converted through photosynthesis to drive biological processes. Any life on rogue planets would need to evolve alternative energy sources, possibly utilizing chemosynthesis similar to organisms found near Earth's hydrothermal vents. Such life would likely be limited to simple, microbial forms unless some other energy-gathering mechanism could evolve. Despite these challenges, the sheer number of rogue planets in our galaxy suggests that even if only a tiny fraction maintain conditions suitable for life, the total number of potentially life-bearing worlds could be significant. Furthermore, some scientists speculate that rogue planets might actually provide more stable environments for life in the long term than planets orbiting stars. They would be free from the harmful effects of stellar radiation, safe from devastating solar flares, and immune to the life-challenging variations that come with orbital cycles. The study of potential life on rogue planets also forces us to broaden our definition of habitability. As we discover more extreme environments on Earth harboring resilient life forms, we must remain open to the possibility that life might exist in conditions far different from those we consider habitable based on Earth standards. This expanded perspective is crucial as we continue our search for life beyond our solar system, reminding us that life, should it exist elsewhere, might thrive in environments we can barely imagine. The sheer scale of rogue planets in our galaxy presents a mind-boggling picture that challenges our traditional understanding of cosmic populations. Recent astronomical surveys and theoretical models have revealed numbers that would have seemed impossible just a few decades ago. Current estimates suggest that the Milky Way could harbor an astounding number of rogue planets, potentially ranging from 100 billion to several trillion wandering worlds. To put this into perspective, our galaxy contains approximately 400 billion stars, meaning there could be up to 10 rogue planets for every star in the Milky Way. This vast population of cosmic wanderers represents a hidden mass of planetary bodies drifting through the interstellar void. The mass distribution of these nomadic worlds spans an incredible range. At the lower end of the spectrum, we find planets smaller than Mars, with masses less than 0.1 Earth masses. These small wanderers likely represent rocky worlds that were violently ejected from their original solar systems during formation. At the upper end, we encounter superjovian behemoths, with masses up to 13 times that of Jupiter. Beyond this mass threshold, objects begin to enter the realm of brown dwarfs, often called failed stars. Particularly intriguing are the concentrations of rogue planets found in certain regions of our galaxy. Young star clusters have proved to be especially rich hunting grounds, with some studies suggesting that free-floating planets might outnumber stars by a factor of 2 or more in these regions. The Orion Nebula cluster, for instance, has revealed a surprising abundance of planetary mass objects drifting between its stars. The numbers become even more fascinating when we consider age distributions. Astronomers estimate that roughly 10% of all rogue planets are relatively young, less than 200 million years old. These younger worlds are particularly valuable for study as they still retain enough internal heat to be observable in infrared wavelengths. The remaining 90% are older, cooler objects that have been wandering the galaxy for billions of years, making them much harder to detect with current technology. Size distribution studies have revealed another surprising pattern. There appears to be a higher proportion of Earth-sized rogue planets than previously thought. While initial discoveries focused on Jupiter-sized worlds due to observational bias, improved detection methods suggest that smaller, rocky planets might actually be more common among the rogue planet population. Some estimates indicate that there could be billions of Earth-mass rogue planets in our galaxy alone. The spatial distribution of these cosmic wanderers adds another layer of intrigue. Unlike stars, which generally follow orderly orbits around the galactic center, rogue planets can follow highly eccentric paths that take them far above or below the galactic plane. Some may even escape the galaxy entirely, becoming intergalactic wanderers. Calculations suggest that anywhere from 5% to 15% of all planets formed in the Milky Way may have been ejected into intergalactic space over the galaxy's lifetime. Recent studies of rogue planet velocities have yielded fascinating data. While most stars in our galaxy orbit the center at speeds of about 200–250 kilometers per second, rogue planets have been observed moving at various speeds from as slow as 10 kilometers per second to hyperbolic velocities exceeding our galaxy's escape velocity. These varying speeds tell different stories about their origins and ejection mechanisms. The mass census of rogue planets also provides crucial insights into planetary system formation efficiency. The total mass of all rogue planets in our galaxy could equal or exceed the mass of all planets currently orbiting stars. This suggests that planetary system formation is an incredibly wasteful process, with as much material ending up in ejected planets as in stable orbital configurations. When we extrapolate these numbers to the observable universe, the figures become truly astronomical. With an estimated 2 trillion galaxies in the observable universe, the total number of rogue planets could exceed 1024. That's a 1 followed by 24 zeros. This means there are more rogue planets in the universe than there are grains of sand on all of Earth's beaches combined. These staggering numbers remind us that our cosmic neighborhood is far more densely populated than we once imagined. The space between stars, far from being empty, is dotted with countless wandering worlds, each carrying its own story of formation, ejection, and solitary journey through the cosmic deep. The quest to understand rogue planets is entering an exciting new era, with several groundbreaking missions and observatories on the horizon that promise to revolutionize our understanding of these cosmic wanderers. These ambitious projects represent the cutting edge of astronomical technology and human ingenuity. The Nancy Grace Roman Space Telescope, formerly known as the First, stands as NASA's next flagship observatory after the James Webb Space Telescope. Scheduled for launch in the mid-2020s, this revolutionary instrument has been specifically designed with rogue planet detection as one of its primary objectives. The Roman telescope's wide-field instrument will survey vast regions of space, monitoring hundreds of millions of stars simultaneously for microlensing events. Its exceptional sensitivity and stable space-based platform will allow it to detect planets as small as Mars, potentially discovering thousands of rogue planets during its mission. Scientists estimate that Roman could identify over 250 rogue planets through microlensing, providing the first comprehensive census of these wandering worlds. The European Southern Observatory's extremely large telescope, currently under construction in Chile's Atacama Desert, represents another quantum leap in our planet-hunting capabilities. With its colossal 39.3-meter primary mirror, the ELT will collect more light than all current major ground-based research telescopes combined. This unprecedented light-gathering power, coupled with advanced adaptive optic systems, will enable direct imaging of some rogue planets. The telescope's instruments will be capable of analyzing the atmospheric composition of these worlds, potentially revealing their formation history and current conditions. The ELT's extreme sensitivity might even allow us to detect water vapor or other biomarkers in the atmospheres of the largest rogue planets. Space-based interferometry projects represent the next frontier in rogue planet detection. The proposed Origins Space Telescope concept would combine multiple telescopes working in perfect synchronization to achieve resolution far beyond what's possible with a single instrument. This technology could potentially map the distribution of rogue planets throughout our galactic neighborhood with unprecedented precision. By measuring their velocities and trajectories, we could reconstruct their histories and understand the mechanisms that launch them into interstellar space. The Large Interferometer. For Exoplanet's mission concept, under study by the European Space Agency, proposes a constellation of space telescopes working together to conduct detailed surveys of nearby planetary objects, including rogue planets. This mission could potentially characterize the atmospheres of these wandering worlds with extraordinary detail, providing insights into their composition and potential habitability. Ground-based survey networks are also evolving to meet the challenge of rogue planet detection. The Vera C. Rubin Observatory, with its massive 8.4-meter mirror and revolutionary 3.2 gigapixel camera, will conduct the legacy survey of space and time, scanning the entire visible sky every few nights. This unprecedented survey will likely discover numerous bright microlensing events caused by rogue planets, adding significantly to our census of these objects. Artificial intelligence and machine learning algorithms are being developed to sift through the enormous amounts of data these missions will generate. These tools will be crucial in identifying the subtle signatures of rogue planets in microlensing events and direct imaging data. The development of these automated systems represents a crucial component of future detection efforts, as the volume of astronomical data continues to grow exponentially. International collaboration plays an increasingly important role in these future projects. The Global Microlensing Network, a proposed expansion of existing microlensing surveys, would coordinate telescopes worldwide to provide continuous monitoring of potential microlensing events. This network would ensure that no rogue planet detection opportunity goes unnoticed, regardless of where and when it occurs. These future missions will not only increase our catalogue of known rogue planets, but also provide unprecedented details about their properties. Advanced spectroscopic capabilities will reveal their atmospheric composition, internal structure, and formation history. For the first time, we'll be able to create detailed demographic profiles of the rogue planet population, understanding their distribution by mass, age, and composition. The next decade promises to be transformative in our understanding of these cosmic wanderers. As these ambitious projects come online, we stand on the brink of discoveries that will reshape our understanding of planetary formation and evolution. The secrets of these lonely worlds are about to be unveiled, offering new insights into the dynamic nature of our galaxy and the countless worlds it contains. The study of rogue planets presents astronomers and planetary scientists with a series of fascinating challenges and unresolved questions that continue to push the boundaries of our understanding. These cosmic wanderers challenge our definitions, detection capabilities, and fundamental theories about planetary systems and life itself. One of the most persistent challenges in rogue planet research lies in the fundamental question of classification. The boundary between massive rogue planets and low-mass brown dwarfs remains frustratingly blurry. While we generally consider 13 Jupiter masses as the theoretical dividing line where deuterium fusion becomes possible, nature rarely respects such clean categorical boundaries. Objects near this mass threshold may exhibit characteristics of both planets and brown dwarfs, making classification particularly challenging. Without knowing an object's formation history, determining whether it formed like a planet through core accretion or like a star through gravitational collapse becomes nearly impossible. This classification challenge affects not only our understanding of individual objects, but also influences our statistical analysis of planetary populations. The true abundance of rogue planets in our galaxy remains one of the most intriguing open questions in modern astronomy. Current estimates vary widely, ranging from one rogue planet per star to hundreds per star. This uncertainty stems from several factors: our limited ability to detect smaller rogue planets, observational biases in our detection methods, and the challenge of extrapolating from limited survey data to galaxy-wide populations. The microlensing surveys that have provided most of our rogue planet detections are inherently biased toward finding larger objects, leaving us with an incomplete picture of the smaller Earth-sized wanderers that might be far more numerous. Perhaps one of the most captivating questions concerns the potential habitability of these lonely worlds. While conventional wisdom suggests that planets need stellar energy to maintain conditions suitable for life, several theoretical models propose mechanisms through which rogue planets might maintain potentially habitable conditions for extended periods. Internal heat from radioactive decay, coupled with thick hydrogen-rich atmospheres, could potentially create greenhouse effects powerful enough to maintain liquid water beneath frozen surfaces. However, the long-term stability of such conditions remains uncertain. We still don't fully understand how atmospheric composition might evolve over billions of years without stellar input, or how internal heat sources might decay over time. The origin and evolution of rogue planets pose another set of compelling questions. While we have identified several mechanisms through which planets might be ejected from their solar systems, we don't yet know the relative importance of each mechanism. Are most rogue planets violent ejectees from unstable young solar systems, or do they form independently in isolation? The answer could dramatically affect our understanding of planetary system formation and evolution. The potential for rogue planets to host complex chemical processes presents another frontier of investigation. Without stellar radiation to drive photochemistry, what alternative chemical pathways might emerge? Could other energy sources, such as cosmic rays or internal radioactivity, drive interesting chemical evolution? These questions touch on fundamental aspects of prebiotic chemistry and the origins of life. Movement and distribution patterns of rogue planets through the galaxy represent another poorly understood aspect. Unlike stars, which generally follow predictable orbital paths around the galactic center, rogue planets might traverse the galaxy in much more chaotic patterns. Understanding these movements could help us better comprehend galactic dynamics and the distribution of mass throughout our cosmic neighborhood. The detection of smaller rogue planets remains a significant technical challenge. While we've made great strides in identifying Jupiter-sized wanderers, Earth-sized rogue planets continue to elude our best detection methods. Developing new techniques and technologies to find these smaller worlds represents a crucial next step in understanding the full spectrum of rogue planets. Another intriguing question concerns the potential for rogue planets to be captured by other stellar systems. While we understand the basic physics of such captures, we don't know how frequently they occur or what role they might play in the evolution of planetary systems. Could some of the unusual planetary configurations we've observed around other stars be explained by captured rogues? The survival of satellites around rogue planets presents another fascinating area of study. Could moons remain bound to ejected planets? If so, how might the parent planet's ejection affect these satellites? The possibility of rogue planets maintaining complex satellite systems adds another layer to their potential as habitable worlds. These open questions drive continued research and technological development in astronomical observation. Each answer we find seems to generate new questions, pushing us to explore further and dig deeper into the mysteries of these cosmic wanderers. The realm of rogue planets stands as one of the most captivating frontiers in modern astronomy, challenging our conventional understanding of cosmic architecture while unveiling new chapters in the story of planetary evolution. As we peer deeper into the darkness between the stars, these celestial nomads continue to reshape our perspective on what it means to be a planet and how our universe operates. The discovery and study of rogue planets represent far more than just an astronomical curiosity. These wandering worlds serve as cosmic laboratories, offering unique opportunities to test our theories of planetary formation, atmospheric physics, and even the potential for life in the most extreme conditions. Their very existence forces us to confront the dynamic and often violent nature of solar system evolution, where planets can be torn from their parent stars and cast into the interstellar void. Perhaps most profoundly, rogue planets challenge our Earth-centric views of what constitutes a normal planetary existence. We've long defined planets by their relationships to stars, yet these independent worlds demonstrate that planetary bodies can exist and persist without stellar companions. This realization opens new avenues for considering how and where life might emerge in the universe, expanding our search parameters far beyond the traditional habitable zone concept. The technical challenges of studying these dark wanderers have driven remarkable innovations in astronomical observation and detection methods. From gravitational microlensing to advanced infrared imaging, each new technique developed to study rogue planets has enhanced our broader astronomical capabilities, benefiting many other areas of space science. As we look to the future, the study of rogue planets stands at the threshold of a new era. Next-generation telescopes and detection systems promise to reveal these objects in unprecedented detail, while theoretical work continues to expand our understanding of their potential roles in galactic evolution. The possibility that our galaxy hosts billions of these wandering worlds suggests that we've only begun to scratch the surface of this fascinating phenomenon. These lonely travelers remind us that the universe operates on scales and principles far beyond our initial assumptions. Each rogue planet carries its own unique history, a story of formation, ejection, and solitary journey through the cosmic deep. Collectively, they tell a larger tale about the dynamic nature of planetary systems and the countless paths that planetary evolution can take. Our journey into understanding rogue planets parallels humanity's broader quest to comprehend our place in the cosmos. These wandering worlds remind us that the universe is far more diverse and dynamic than we once imagined, filled with possibilities we are only beginning to understand. As we continue to unlock their secrets, rogue planets will undoubtedly reveal new surprises and insights, pushing the boundaries of our knowledge and imagination ever further into the cosmic unknown. I hope this exploration of rogue planets has expanded your cosmic horizons and ignited your curiosity about the unknown. If you've been captivated by these celestial wanderers, there's so much more to discover together. Hit the subscribe button and activate notifications to join us on future cosmic adventures. Share this video with fellow space enthusiasts who share your fascination with the mysteries of the universe. What aspect of rogue planets intrigued you the most? Was it their mysterious origins, their potential for harboring life, or perhaps their sheer abundance in our galaxy? Share your thoughts in the comments below. I'd love to hear your perspective on these cosmic nomads. Until our next cosmic journey together, remember that in the vast ocean of space, even planets can be solitary sailors, each one carrying its own unique story through the cosmic deep. Thank you for joining me on this exploration, and I'll see you in our next adventure among the stars.